Okay, folks at home, let me know if you can hear me. Also, the chat box is open and we are recording attendance, so go ahead and type. And you can type something, yes, I can hear you. Caden, can you hear me? Okay, great, thanks. Now let's check the settings, output level, okay, good. All right, we're good. Thank you, Luai. I'm gonna have a snack before we start. It's always important to have chocolate chip cookies. Preferably the more the better. Or brownies. Either will do. Mm. Mm. Okay. Well, before we begin, let me check the weather. Just well, I'm not getting any reception. Okay, let's get started. Let's share the screen. I'm gonna do this. All right, well, if you are in today's lab and you are hoping to go to City Park, well, I hope we go too, but I'm keeping a close eye on the weather right now. It's not telling me anything. It's as if there is no weather. But earlier, before I came over here, it was not looking that good. Now, we can work if it is raining lightly. But if it's raining really heavily, we won't be able to identify plants and we won't be able to use the identification guides. And so we may have to cancel that. and I will update you after lecture, apparently when I can get some reception. You know, we may wait until the last minute. I may ask you to just come to 216 and see how things are looking, and we may just send you all home or not. If we don't get this lab done today, you'll get the data anyway, but you can feel free to come on Friday afternoon if you have it open, if you really want to see what's going on. I'm partway through the exam essays, and so we'll have that later this week. Moodle will probably automatically post the grade when it's done. And for some of you who had to do more than one attempt because you got knocked off, that'll be wrong. So I'll have to go in and manually adjust it, okay? So don't take the initial grades too seriously if you had more than one attempt, because Respondus was not cooperating.
I have a question.
Yes.
So on my essay part, it says complete, and then I see like there's 2 questions. I lost some points. So I'm wondering if complete means I got all the points, or if it's just still.
It means that I graded it.
Okay.
It means that I graded it, and I haven't graded the others that are not complete yet, I think.
Okay. So I guess what I'm trying to see if complete means I got all the points for the problem, because the other ones say
I don't
like,
believe so, no.
no.
I think I think all that it means is that I assigned a score and made comments.
Okay, thank you.
Okay. All right, so today we're going to extend our understanding of population growth from the net reproductive rate to the geometric growth rate, which applies to certain populations. And we'll show you how we model that. And we'll give you some examples. And then when you go home, you'll wind up getting some practice problems along with their answers. And once again, try to figure out the problems before you look at the answers. But then we'll look at the kind of population growth that applies to other kinds of populations, which is exponential growth. We'll show how the two are related. And so since geometric growth is related to the net reproductive rate, and exponential growth is related to the geometric growth rate, they're all the same thing, basically. We just express them differently because they help us understand different kinds of populations better or worse. And then we'll look at one kind of alternative formulation of exponential growth, and then we'll summarize how they're all related. And this is a fairly involved set of ideas. So it's going to take some work for you to master them. Okay, but at the minimum on the exam, you'll be expected to be able to work with the geometric growth rate, the exponential growth rate. You'll need to be able to understand how they're related to one another and make some calculations that allow you to convert one into the other. So pay attention, and you'll have practice problems after class. So first, let's look at the relationship between the net reproductive rate and the geometric growth rate, lambda, as we call it. So this is reasonably straightforward. R sub 0 is the total number of offspring produced by an individual in a lifetime, whereas lambda is the average number of offspring produced in a given interval. Okay, and that's usually going to be a year for our purposes. Now, if an organism lives exactly 1 year, R sub 0, the net reproductive rate, is exactly the same as the geometric growth rate, because a lifetime lasts a year. And lambda is measured typically over a year. So for annual organisms, the net reproductive rate is the geometric growth rate. But what if you live longer than 1 year? and you reproduce at maybe different rates in different years. Like that sample life table we had where you reproduced more at later ages. All right, well, then it's not entirely clear what the average reproduction of an individual is going to be in a given year. You have to sort of work that out. So for those kinds of populations that live more than 1 year, we need to know the generation time in order to convert the net reproductive rate R sub 0 into an annual reproductive rate. Okay, but if we find the generation time, which is the average amount of time that elapses between an organism being born and an organism reproducing, then lambda is simply R sub 0 raised to the 1 over T power. Okay, now ecology courses often just give people these formulas and say, okay, just memorize this. I don't do that. I try to help you see how we get that. So what I'm going to do now is walk you through this exactly the way we walked through how we calculate life expectancy and reproductive value in the life table. Okay, at the end of the day, you have these formulas, but then what I'm trying to do is show you how we get them. So here's how we get them. So for this little life table, R sub 0 is 1.8, right? That's the lifetime reproduction. Okay, but what we want to know for working with populations themselves, not individuals, is what we can expect individuals to do in a given year. So we have to adjust this net reproductive rate so that it gives us not a lifetime reproduction, but an annual average reproduction. Excuse me. So what we need to do is to look at this life table and see that there's not equal amounts of reproduction in the different years. And so what we have to do is adjust the reproduction in a given year for the year in which it occurs. So you'll notice here that we have the expectation of producing 0.4 offspring in year 2 and 0.9 offspring in year 3. So on average, the average reproduction of an individual is going to be weighted more towards the latter part of its life than the early part of its life. So let's show you a slightly simpler set of numbers where it's a little easier to calculate this. And here we go. Here's a little life table that shows you the whole thing. So what we want to know is what the average age is that an animal reproduces. And so the way we find that is by asking, well, how many offspring does it produce at a given year? And how many years did it live to produce them? So you find the generation time by using those two pieces of information. And the formula is LXBX times the age X divided by LXBX. So that's up here at the top for those of you at home. So LXBX, that's the expectation of reproducing at a particular age, times that age, divided by LXBX. All right, so let's then look at this. Well, we're looking for the sum of these things. So the sum of LXBX times X for all ages X, and we're looking for the sum of the LXBX column, which is just that reproductive rate down here. Okay. All right, so how we calculate this then is, let's say we expect to produce 0.5 offspring in year 1. All right, well, 0.5 is LXBX times the age, which is 1. So LXBX is 0.5 times 1 times 1 is 0.5. So that's our first piece of information. The second piece of information is that in this population, we expect to produce, 0.4 offspring in year 2. So LXBX is 0.4 times 1, and in the second year, times 2. So what we're doing is weighting the reproduction that this individual does by the time that it does it. So here we have 0.4 in year 2, and that means that we're weighting this differently than the 0.5 in year 1. Okay, and then the third year, which is our last year in this life table, we have LX of 0.3, BX of 0.2 times year 3. So it's 0.3 times 2 times year 3, which is 1.8. Right, so all we're doing is taking the LX times BX and multiplying it by the year in which that happens. So 0.5 times 1 in year 1 is 0.5. 0.4 times 1 in year 2 is 0.8. And 0.3 times 2 in year 3 gives you 1.8. So
And
the
this would be
sum,
given, right?
sorry?
This would be given?
Yes.
All right.
Yeah, you have to have the life table values to know this. So the sum of LXBXX for this little sample is 3.1. And the sum of LXBX is 1.5. So this particular organism produces an average of 1.5 offspring in the course of its lifetime. And it does it kind of over the period of 3.1 years. So it took 3.1 years to produce 1.5 offspring. The average then is that this organism produces offspring at 2.07 years. Here, let me silence that. Sorry about that. Okay, so the average time that elapses between the birth of this organism and its average reproduction is 2.7 years. You can see that it produces some offspring in year 1, but it produces more offspring in years 2 and 3. So the average time between birth and the average reproduction in this organism is not 1 year, it's 2 years, 2.07. So the generation time is 2.07 by our calculation. And what that means is that we can now convert R sub 0 into an annual expected rate. So, and this is how we do it at the bottom here, 1.5 raised to the 1 over g power. So 1.5 raised to the 1 divided by 2.07 is 1.5 raised to the 0.483 power. And the annual reproductive rate then that we expect is about 1.22. So down here at the bottom, guys at home, that's what we're doing here. 1 over g, we've calculated the generation time as 2.07. 1 over 27 is the power that we raised the reproductive rate to. And that means that 1.5 raised to the 0.483 power is 1.22. So the annual reproductive rate is expected to be about 1.22 offspring per year for the population. Because some of these individuals are in year 0 and they're not reproducing at all. Some of these individuals are in year 1 and they're producing, on average, half an offspring, right? Because we use not BX, but LXBX. Some of these individuals are in year 2 and they're producing, on average, 0.4 offspring. And then some of these individuals are in year 3 and they're producing, on average, 0.6 offspring. So based on this schedule, the average reproduction per year, including the 0-year-olds that aren't reproducing, the 1-year-olds that are producing half an offspring, the 2-year-olds that are producing 0.4 offspring, and the 3-year-olds that are producing 0.6 offspring. That average then is 1.22 offspring per year. So that's the relationship between the net reproductive rate and the annual reproductive rate, lambda. So this geometric reproductive rate, lambda, is directly obtained from the life table, if you need to. Now, it's pretty important to understand how this geometric growth rate works. So, So this is what happens over time if you have a stable geometric growth rate. And remember, in order to have a constant lambda, you must be at a stable age distribution. But if you're at a stable age distribution, then you simply multiply the number of organisms at any given time times the growth rate, lambda, and then you can calculate the number of organisms that you'll have in the next time step. Now, since you're multiplying lambda by an increasing number of individuals, so we start out fairly low here, but every time you're multiplying the number times some constant factor, meaning that the next number is bigger and bigger and bigger and bigger, you're multiplying lambda times a larger and larger number each time. So this curve is going to bend upwards because you're getting more and more organisms reproducing at this constant rate. So here you might have 100 at the beginning, and here by time 6, you probably have about 200. Well, 100 times 1.22 is 122, but 200 times 1.22 is 244. So this curve of the population size, which is n, will bend upwards over time because more and more organisms are reproducing, and you're getting more and more added each time period. Here, at the start, if you had 100, you added 22 individuals. But out here at time 6, if you had 200, you added 44 individuals. So it's a larger and larger number being added each time step. So what we can do is look at how this works, all right? We're going to look at N2 and N1, all right? So the number that is added between time 2 and time 1 will be a certain number. I'm not going to bother you with that, but the number that's added between time 6 and time 7 is a larger number because there are more individuals reproducing at time 6 than at time 1. It's just a larger number. This population is growing. But if you are at a stable age distribution, even though the numbers are larger at later times, the ratios are identical. Remember from last time we looked at the ratio of population size at any 2 times. And once you reach a stable age distribution, it becomes constant. So the population grows over time, and the number that is added to the population at any given time grows, but the ratio of population size at any two adjacent time periods becomes constant if you have a stable age distribution. So N2 minus N1 is a smaller number than N7 minus N6 because you're adding more individuals at time 6 than at time 1. But the ratio of the sizes is the same. N2 divided by N1 will be lambda. And N7 divided by N6 is also lambda because the ratio is the same. You're multiplying these numbers by the same factor. In our little example, it was 1.22. So if you multiply 100 times 1.22, it's 122 individuals. Well, 122 divided by 100 is 1.22. At time 6, we suggested you might have 200 individuals. Well, 200 individuals times 1.22 is 244. 244 divided by 200 is 1.22, the same ratio. Lambda is constant at a stable age distribution. So although the absolute numbers added to the population increase every time, the ratio of any two population sizes is the same. So here we're showing you one more time. B is larger than A, the difference here between the two adjacent populations, because there are more organisms reproducing at B than at A. But the ratios are identical because you're simply multiplying N1 times the same amount as you are N6. N1 times 1.22 gives you N2. N6 times 1.22 gives you N7. So it's the same ratio. Once you reach a stable age distribution, lambda becomes constant. And that's why we went through that exercise of projecting the life table to show you that lambda does stabilize the ratio of any two populations. So we can now work with lambda if we make that assumption. So if the ratio between n at t plus 1 and n at t is lambda, then n at t plus 1 equals n at t times lambda. Duh, what we've been saying for 2 days now. But similarly, if n1 equals n0 times lambda, then n2 equals n1 times lambda. And n3 equals n2 times lambda. We're just multiplying each population by lambda to get the next population size. So n0 times lambda is n1, and 1 times lambda is n2, and 2 times lambda is n3. But hey, you can substitute because n1 is n0 times lambda. So n2 is not just n1 times lambda, it's also n0 times lambda times lambda. It's the same thing. So n2 also equals n0 times lambda squared. Now notice that you got 2 time steps into the future, and you're just multiplying the beginning population by lambda. So notice that the number of time steps you want to go out is equivalent to the power that you raise lambda to. And if n3 is n2 times lambda, then that's also n0 times lambda raised to the 3rd power. So we have a general relationship here. the population size at any time t, down here at the bottom now, is equal to the starting population size times lambda raised to the same power of t. So if you want to know the population 10 years into the future, and you have a starting population, all you do is raise lambda to the 10th power and multiply it times the starting population. That'll give you your estimate of the population in 10 years. Because we are simply multiplying the population by lambda every single year. So if our starting population is 100, and we're getting the population at time 1 by multiplying 100 times lambda, then the population at time 2 is 100 times lambda times lambda. Population at time 3 is 100 times lambda times lambda times lambda. So this is a general relationship. If you want to know the population at any time t, raise lambda to that same power and multiply it times the population you're starting, and you get that. The backwards thing also works, because if you have a population at some time and you want to know the starting population, you can take the root of lambda and figure that out backwards. And I'll show you how that's done in just a second. All right, so let's do a quick example here. If n sub 0 is 20 and n sub 1 is 28, what's lambda? Well, okay, so it's n1, which is 28, equals n0, which is 20, times lambda to the 1 power, since you're asking for 1 year or 1 time step. So 28 equals 20 times lambda, and you just do the algebra. 28 divided by 20 is 1.4. So lambda is 1.4. This is the kind of question you're going to get on the exam. How do you work with lambda? How do you calculate a population size? Or given 2 population sizes, what's lambda? Okay, a little bit more complicated. Aha. So we have a starting population of 60, and we have a population 2 time steps later of 135. What's lambda? Well, it's the square root of the ratio now, because it's 2 time steps. So n2 equals n0 times lambda squared, because it's 2 time steps into the future. Whatever the geometric growth rate is, we multiplied it once to get the population at time 1, and then we multiplied that population by lambda again to get time 2. So it's n0 times lambda, or lambda squared. So all you do then is set up the equation here. 135 equals 60 times lambda squared. And then you take the ratio, 135 divided by 60 equals lambda squared. Okay, and that means that 2.25 is lambda. Notice it's easy numbers. If you find that you are working with complicated numbers on an exam, you did it wrong, because I don't like complicated numbers. Well, what's the square root of 2.25? It's 1.5. So in this case, lambda is 1.5. And if you need to prove that to yourself, ask yourself, what's the product of 60 times 1.5? It's 90. That's the population at time 1. What is the product of 90 times 1.5? That's n1 times lambda. Well, it's 90 plus 45, which is 135. So it actually does work. Okay, so you're gonna want to look at the problems, because they will be exactly like the problems you'll get on the exam. So this is how we work with geometric growth. We can estimate what a population size is going to be far into the future by taking lambda to whatever time period that is, and multiplying it by an initial population size. Now, this works for some populations, but not others. So it works for populations that have a discrete reproductive season. Think about deer. Deer reproduce in the spring every single year, and no deer reproduces outside of the spring. So there is no reproduction of deer populations in June, July, August. It's only once per year, and everybody does it simultaneously. That's what we use geometric population growth for, to model those kinds of populations. What about us? We don't have a breeding season. We reproduce continuously. Bacteria reproduce continuously. The geometric model is not good enough for us because we can ask about any time interval and have a meaningful question. You can't ask what's the population of deer in, say, March, and then ask what is the population in October and try to use the geometric growth rate, because that's not the way it works. They don't reproduce. You could ask about what their population is the following March, but not in October. For people, bacteria, and all of the continuously reproducing species, we need to be able to ask what the population size is at any given time period in the future, not just a discrete interval. So any interval, no matter how small, is fair game for a species like us. And that means that we need not a geometric model, but an exponential model. So we have a dotted line here indicating the intervals on the left. And over here on the right, we have a continuous line indicating that we can ask what the difference in population size is at any interval. Now, this is probably starting to sound alarmingly like a calculus problem, and it is. So if you are allergic to calculus, just bear with me. I'm going to show you how we get this equation using a little calculus trickeration, but we're not going to do more than that. Once we get this, once I show you that this is not magic, that it actually comes from somewhere, we will more or less forget about it and just work with the equation. So the increase in population in a continuously reproducing species is exactly the same as the increase in your bank account that is compounding interest. Now, what's the interval over which you're compounding? Well, if you know anything about your savings account, maybe none of you do, but your bank can compound your interest once a year. So that's annual interest. That's geometric growth. But it can also compound it every 6 months. You get a little bit of extra population growth if you're compounding at 6 months. But you can also compound monthly or daily or instantaneously. The interval over which you compound simply factors into the interest rate. And it factors in this way. So to calculate a population at time t with a starting population here, you would multiply n sub 0 times 1 plus the interest rate, okay, raised to the power of the number of years. Okay, and the interest rate might be 22%, like in our example. Our geometric growth rate was 1.22. That is what we're talking about. But if you're compounding it, then you divide the annual rate by the number of intervals in which you're compounding. So instead of 22% annually, it's 11% every 6 months. But then you have to adjust the number of times you compound. So down here at the bottom is our formula for compound interest. The interest rate is I. Q is the number of compounding intervals. Could be 2 if it's every 6 months, 4 if it's quarterly, 365 if it's daily, or infinity if it's infinity. And then it's raised to the power here. Here's the time that you're interested in times the number of compounding intervals. This is exactly the same in population growth and your savings account. All right, so we've got this complicated thing. Nobody wants to work with this. Ecologists are not any different from you. We don't want complicated stuff. So we're going to simplify this. And we're going to use a trick. We're going to rearrange the way this equation looks. We're going to let that IQ thing that is kind of obnoxious in there at the top, we're going to say, let's call that X. Okay, and then what that means is that Q then equals I divided by X. And we're just going to substitute that into the equation. And you're saying, how did that make it simpler? Because in calculus, the limit of this thing here, 1 plus X raised to the 1 divided by X power, is E, the base of natural logarithms. And see, we rearranged the equation at the top, which is right here for you at home, to look like this when we made our substitution. What do we got in there? We've got 1 plus X raised to the 1 divided by X power. But that's E. We know what that is. And so we can get rid of this thing and just call it E. So the number of organisms at any time t in a continuously reproducing population is the starting number times E raised to the IT power. That's how we get this equation. And now you can forget all the steps that we went through because we're just going to work with this equation. But I don't ever just give you something and say, memorize it. I want you to know where they come from. So we don't use I because that's money. And we don't think very highly of economists. So instead, we substitute R. And R is for reproduction. And so our equation at the end of the day for continuous population growth is N at time t equals the beginning population N sub 0 times E to the RT, where R is the population growth rate. This allows us to use calculus without even knowing it, because you've got a calculator that does this for you automatically, to ask what the change in population will be at any given time, over any period of time. 6 months, 19.8 months, doesn't matter. For continuous population growth, this is a meaningful question. For geometric population growth, it is not. Okay, now, lambda and R are related, and you can clearly see that if you just look at the two equations. Get a load of those two equations. On the left is geometric growth. N sub t equals N sub 0 times lambda raised to the t power. On the right is the exponential growth equation. N sub t equals N sub 0 times e to the RT. Well, okay, everything's constant in there except one thing. And at the bottom, you can see what those things are. If we set these two equations equal to each other, because N sub t is, you can just say, well, they're both equal to N sub t, so let's set them equal to each other. We can cancel out the N sub 0s, and then we get lambda t equals e to the RT. We can cancel the t in the exponent, and we get lambda equals e to the r. We know what that is. The natural logarithm of lambda equals the exponential growth rate. They are the same thing. They're exactly the same. So we can get a life table measure the net reproductive rate, R sub 0. We can calculate from that the geometric growth rate. And if it's a continuously reproducing population, we just convert it into the exponential growth rate. They're the same thing. And this will be something that I'll expect you to know on the exam also. I'll expect you to be able to use the geometric equation to figure out population sizes, the exponential growth equation to figure out population sizes. So you'll want a scientific calculator that allows you to do that. And I'll expect you to know how to convert lambda and R. And you get questions about all of those for practice. Okay. Now, what happens when we have a stable population that is neither growing nor declining? What would be our value of lambda and what would be our value of R? Well, all right. Lambda is defined as the ratio of n sub 1 divided by n sub 0. So if the population is not growing, those two numbers are the same. If the starting number is 100 and the population is not growing, then at the next time step, the population is still 100. 100 divided by 100 is 1. So a lambda value of 1 means that the population is stable. If the population is growing, lambda will be greater than 1. If it's declining, it will be less than 1. What about the exponential growth rate? This is a little more complicated. Okay, but since lambda equals 1, we know that e to the r is lambda. And that means that e to the r is 1. And so the natural log of lambda then would be the answer to what the population growth rate is when the population is stable. The log of 1 is 0. So the exponential growth rate for a stable population is 0. If little r is greater than 0, the population is increasing. If little r is negative, the population is declining. And it's very important that you understand that relationship. Understand what those numbers mean. When r is 1, when lambda is 1, when lambda is greater than 1, when lambda is less than 1, when r is 0, when r is less than 0, when r is greater than 0. And that makes sense that r should be 0 for a stable population, because the number at any time t should equal the number that you start with times e to the rt. If that's stable, then e to the rt has to wind up equaling 1. Okay, and e to the 0 power is 1. So, all right, last thing about these population growth metrics is that we often use the change in population size, which is given by the slope of the curve, rather than that e to the rt equation, because who doesn't like a graphical representation that you don't have to do math on? So yeah, we often talk about this. So the change in population size is given by the slope of the exponential growth curve. And remember, if you have few organisms reproducing, you don't have a high change in the population, you have a low slope. If you have a lot of organisms, that's down here. If you have a lot of organisms reproducing here, then the change from one time to the next will be high because you're adding lots of individuals to the population. Okay, well, the slope of this line is given by the derivative of that equation. Oh my God, another calculus thing. except that we're not going to do anything with it except explain that the derivative is dn dt, the change in numbers for a given change of period in time, is equal to r times n. That's the derivative of that thing. Doesn't that look more inviting than n sub 0 times e to the rt? Yeah, it does. And we make use of this over and over and over again. Over the next month, you will be so familiar with this, I hope. Okay, so the only reason that this slope changes is because of the number of organisms reproducing, because r is a constant. At least right now, r is a constant. We'll see that r can be modified, but not yet. So dn dt is the slope of the exponential growth line. It is the fourth thing that we will work with in this class. We work with r sub 0, the net reproductive rate. We work with lambda, the geometric growth rate. We work with little r, the exponential growth rate. And we work with dn dt, the slope of the exponential growth line. And here's a summary of them. So net reproductive rate is an individual measure. It's the lifetime reproduction of an individual. Lambda is the geometric growth rate. It is a population thing. It is the ratio of population sizes at any two times. And it is related to r sub 0 if you know the generation time. 1 divided by the generation time is the power that you raise r sub 0 to convert it into lambda. Okay, lambda also equals e to the r. You need to remember that there's a straight across conversion between exponential and geometric growth. You need to be able to convert one to the other quickly and easily. You need to recognize when a problem is asking you to use the geometric growth rate and when the problem is asking you to use an exponential growth rate. Okay. So r is the exponential growth rate for continuously reproducing populations. It is the natural log of lambda. And then finally, the last thing, dn dt is the instantaneous rate of increase. It's the slope of the exponential growth line at any given point in time. And it's equal to r times the number of individuals reproducing. Okay, so this take-home slide here is your study guide for literally the next 6 weeks, because we're going to use these over and over again. All right, I've thrown a lot at you. This is by far the worst of the quantitative stuff that you're going to get crammed with in a given lecture, but it's an important set of information because we will use it over and over again. So it will be really important for you to go back and review this presentation in order to understand what we are doing and where it comes from. All right. This is all I have for today. If we have any questions, I will take them. Yes, we have a question. Will the next exam be definitely what? In person? Yes, the next exam will be in person, partly because of the unfortunate cheating that I caught on the online exam. I shall have more to say about that to whoever is involved. Okay. Any questions at home? All right, guys, I'm going to stop the share. If you are in the lab today, look at your email, because I will tell you, hey, we're going, or hey, we're not going. If I don't tell you we're not going, then at least meet in 216 and we'll see if we're going. All right, logging out here.